Thanks, Lenka. Thanks a lot for the invitation. It's great to be here. So it's been about 2 to 3 years. I think it was in 2020 when I visited here, and that was the time I was trying to understand the first gradient step in training a two-layer neural network. So it's been a long time, and then now today I'll tell you about what happened after polynomially more steps. Okay. By the way, feel free to stop me anytime during the talk. I think I was rushing the slides, so there could be many typos and stuff. So if you don't understand anything, please stop me. Okay. So I want to talk about two works. They have almost identical messages, but they have completely different proof strategies. So the first paper is with Yunwei, Ishan, and Jason at Princeton. And the second paper is with Gerard at NYU and Murad and Mert at University of Toronto. So in both cases, we study the SGD learning of a two-layer neural network, where the difference is that the first paper studies a case where the information exponent is high, and the second paper is just about the quadratic case. Okay. Okay, I will motivate the problem setting using some screenshots from OpenAI. So this is it has been observed in many empirical works that as I increase the scale of my model, the loss, this is usually for pre-training, is going to follow a predictable power law decay. This is referred to as a neural scaling law. So the functional form is usually like the loss is proportional to 1 over data plus 1 over model size. So so basically there's a statistical bottleneck and there's an approximation bottleneck. This is usually interpret this. So this paper, this figure come from Kaplan et al., one of the earlier scaling law papers, where you see that as you increase the compute or the scale of the model, the Pareto frontier of the basically the compute optimal loss is rather predictable. It follows this particular functional form. And then there's another line of works that this is usually not for pre-training, but there's a that reports the behavior of the model performance when you evaluate it on individual tasks. So this is typically, so these figures are not for the pre-training loss, but for the model performance on like solving a specific type of math problems. And here the model performance usually exhibits some sort of transition. So you do not see smooth change with scale. Instead, it seems that the model subtly picks up a capability at certain scales. So this is referred to as emergent capabilities. Okay, so this is not less predictable, and this looks very different from this smooth power law decay in the overall pre-training loss. So there is a pretty clean theoretical model that tries to reconcile this smooth power law decay in the loss and the sort of sharp transition in the acquisition of individual skills, which is this additive model sort of formulation. So the idea here is that the cumulative objective, so the overall loss that I'm optimizing, can be decomposed into like a lot of distinct skills or tasks. Okay, and the learning of each of these tasks can exhibit sharp transitions. But then because my loss is a sum over a lot of these emergent curves, and if they emerge at different time scale, I will have an overall like a smooth power law decay. So this is sort of illustrated in this figure. So if I look at the learning of each individual skills, then I'm going to have a plateau, and then the loss drops. Right? But then because my loss is a sum over all of these, then it looks smooth. And there's been prior works that try to derive the power law rates under this assumption, where the assumption is that the loss can be decomposed into a bunch of completely like independent and decoupled scales, so they don't interact. And so the goal of our work is to sort of provide some justification of this hypothesis in SGD learning of a two-layer neural network, because a priori it's not clear if, because usually we're just given one loss that the model optimizes. It's not clear if such a decomposition exists, and it's not clear if your loss can be decomposed into a bunch of things that are totally independent, right? So we don't have the loss is not a sum of a bunch of like independent losses. So why do we study this SGD learning? It's because in fact in the more practical settings, the existence of emergent risk curve is somewhat controversial. Right? It's been debated on like whether like this could depend on the loss metric. If you change the loss, you would see something that looks fundamentally different. So it's kind of, there's still a lot of discussion on how universal these emergent risk curves is. But in the context of SGD learning, especially feature learnings in high dimension, emergent risk curves are real. And in fact, most of the works in gradient-based feature learning in the past 2 or 3 years exhibit would tell you that the loss kind of behaves like this emergent or the staircase slice, like exhibit this sort of structure. So to provide more context, so let's first consider learning of one neuron. This is a single index model, and so the target function is depends on the projection of my input x, the axis unstructured, this is just isotropic Gaussian, onto one direction, theta. And then there's a nonlinear activation function, like a link function applied on top. This is just one neuron. And so this has been studied in many works on gradient-based feature learning because an efficient algorithm need to discover sort of this low-dimensional structure. Whereas if you have a fixed feature model, like a kernel model, then you're not able to adapt to this sort of low-dimensional structure, so the sample complexity is worse. So the complexity of gradient-based learning with this particular single index function is often governed by the quantity known as the information exponent. So for that, I'll need to define the Hermite expansion of this nonlinear link function sigma star. Okay, so I can write it in the Hermite basis, and I have a bunch of Hermite coefficient alpha j, and the information exponent is defined to be the smallest. Sorry.
Yeah, so you don't have noise in the model?
That's a good point. For the majority of this talk, we'll assume the noiseless model. So you can add, you can also introduce additive label noise. And in fact, I don't think that will change any convergence rate, any scaling results. This, yes, but this is right now. This is noiseless model. So the information exponent is defined to be the smallest integer, such that the Hermite, the smallest integer k, such that the k's Hermite coefficient is non-zero. Okay, and I guess this might be a recap for many of you. So the intuition is that this quantity captures the amount of signal you have in the gradient around random initialization, and you can see this from a standard Stein's lemma type of calculation, where you first approximate the gradient of the square loss with a correlation. And then if you Stein's lemma the correlation, you get the true direction theta. And then this is the correlation of two sort of single index models. And the Hermite expansion will tell you that this can be written as, at least at the population level, as a sum over the inner product raised to some power. Okay. And now if the information exponent is k, that means all the first k minus 1 term in the sum is going to be 0. And then your first, and this inner product is going to vanish in high dimensions. So now if the information exponent is high, the expected magnitude of the gradient is small. Therefore, you will need more samples to concentrate. So there's been many works that show that if you train a two-layer neural network to learn the single index target function, you need something like d to the k samples. Right? This could be k minus 1, or could be k divided by 2. Okay. So what's more interesting than the sample complexity is the behavior of the risk curve. So it turns out that the phenomena, if you plot the loss of your SGD iterates, what's going to happen is that most of the samples or most of the optimization time is going to be spent around this equator, where you're basically you're not aligning with the true direction theta. If you look at online SGD in particular, there will be roughly d to the k minus 1 steps where the loss just stays constant. So this is referred to as the search phase. The intuition is that your parameters are sort of at a sort of approximate saddle in high dimension. You spend most of the samples trying to escape the saddle. And after that, the descent phase where the loss drops from say like 1 to 0, it's just going to be it will happen in constant time. Okay, so this is sort of an example of an emergent risk curve where you spend poly d steps in this initial plateau with loss doesn't drop, and then the loss drops sharply at the end. Okay, does this make sense? Okay, so this is sort of an example of emergence. And now, if you remember, this additive model thesis is stating that the overall scaling law is basically a sum of a bunch of individual emergent curves. And now, if learning single index model give me an emergent risk curve, now the target function we should consider for this additive model class would just be a two-layer neural network, right? Because this is a sum of like a bunch of single index models. Okay, so the width of this target function will be m star. Okay, and for each task, the sigma will have information exponent greater than 1. This entails that there will be some extensive search phase before the loss drops for learning each of these tasks. Okay, so each of these learning each of these single index tasks will give you sort of like a plateau. We can modulate the length of this plateau by changing the second layer coefficient of the target network, so that we can generate a bunch of different lengths of plateau. And if we sum them up, hopefully we get a parallel. Okay. To make this work, there are two assumptions that, we need to assume two things about the regime we study. One is the width needs to be somewhat large, right? And it says that because this power law approximation come from this Riemann sum structure. So you need to be able to sum over like infinitely many sort of sharp emergent curves in order to get a smooth power law. Okay, so the width needs to be large. So we look at this extensive width regime. And two, because we would like to assume some sort of power law coefficient potentially on the second layer weights. Therefore, we must handle the setting where the condition number is large, right? Because if AM, the second layer weights, follow a power law, then this condition number, basically the maximum divided by the minimum of the second layer weights is going to be something like poly M. M is a width. And this M is going to grow with D. So this is also poly D. We need to handle a regime where the different, the strengths of the different components might differ at a poly D order. So these are the two technical challenges. Okay, so basically the goal is to sort of characterize the sample and optimization complexity of SGD, and we'll be characterizing two things in particular. One is the sort of this transition point where you suddenly learn like the M's neuron, target neuron, and then the second is the scaling law and the overall MSE loss. Okay, so let me first tell you some prior results we did. This was last year at Code. It turns out that there is a layer-wise training procedure that works if the information exponent is greater than 2. You will get a sample complexity for learning this class of target function that looks like M, the width of the target function, times d to the k minus 1. And this is kind of intuitive because remember, the complexity of learning one single index model is like d to the k minus 1. So you have m of them, so it's like m times this. It's kind of, this is the total, this is like learning ensemble of a bunch of single index models. And n is the width of my student network, right? So my student is also a two-layer neural network with n. And the width is going to scale as m to kappa, where kappa is a condition number. Okay, so if the condition number is constant order, then life is good. Then the width of the student model is just polynomial, it's just poly D. Okay. But if you remember, in order to cover the power law setting, the condition number is potentially like a poly D. You could have unbounded condition number, in which case this the width of the pseudo network would also be a super polynomial. Okay, so in terms of computation complexity, this will be problematic. I'll tell you why this condition number dependence appears. Okay, but at least in the well-conditioned regime, this result already tells you that this extensive width neural network is learnable with a sample complexity that kind of makes sense. You're learning like m single index models. And this complexity is better than kernel method, which depends on the degree. So now everything here only depends on the information exponent k. Okay, and so where does this sample complexity come from? So this the framework is kind of standard in the gradient-based feature learning literature, where we do layer-wise training. Okay, so we have the pseudo model is also a two-layer neural network with capital N neurons, and we first train the bottom layer, the top layer, sorry, the bottom layer, and then the top layer. The goal of training the bottom layer is to have the individual student weights to try to align with each of the teacher direction theta. Okay, and after that happens, you can now you can refit the second layer so that you approximate the nonlinear link function. Okay, and the simplifying assumption is that we assume the second layer weights is very small. So now the squared loss, the MLC loss, is approximated by the correlation loss. Okay, and the nice thing about the correlation loss is that now the different pseudo neurons become independent. They evolve. They don't interact with each other. So we're basically optimizing an ensemble of a bunch of like independent particles, and each of them will try to find some teacher direction. Okay, and so this is how this and I think there's many other works on learning low DMX models that uses a very similar scheme. Okay, and here's how correlation loss works. So assuming that there's no interaction between different neurons, then each of my pseudoneuron, let's say this is at time t, okay, each of my pseudoneuron is going to be attracted to this each of my pseudoneuron is going to be attracted to like a sum of this teacher neuron. Right? So because my target function is the sum over m star single index component, so each of the pseudoneuron will feel a force like towards each of these teacher neurons. So you get the loss kind of look like this. The gradient look like this. So you have the sum over m star correlation term plus some noise that you control using martingale concentration. So why do we make the assumption that the information exponent is greater than 2? Okay, so because intuitively, lower information exponent means that the optimization problem is easier, right? But actually, it turns out that high information exponent makes the analysis much cleaner. The observation is that if k, the information exponent, is sufficiently large, then I can approximate this sum by the max. Okay, so the sum is sort of this is a contribution of all the different teacher like teacher vectors. But if I can replace it with a max, that means I only have to worry about the target direction that's closest to me at initialization. Okay, so assuming the information exponent is large enough, then what's going to happen is that each neuron will just converge to the closest teacher neuron at random initialization. You don't have to worry about all the other directions. So this is a form of like decoupling. Okay, so and it turns out that information exponent 3 is sufficient to show this decoupled dynamics. So if the information exponent is 3 or more, what's happening is that even though each neuron is attracted to all the m star teacher neurons, it turns out that this attraction is just going to be dominated by the closest teacher neuron, and then you're just training a bunch of like independent single index models. Okay, and this is how you establish sample complexity. And so why is this not able to handle large condition number? It's because all my at initialization, the overlap between the student and the teacher model is going to concentrate at basically 1 over d. Right? This is in high dimension, you have at most like log d fluctuation. But if you look at this, the sum, right? The sum is you have the second layer coefficient am times this inner product. So let's say I have 2 teacher neuron where am differs poly d. That means this AM times this inner product is always going to be larger for the large teacher for this larger AM, because this inner product concentrates at 1/d. Okay. In other words, in order to prevent all the pseudo neuron from converging to the same, like to the large second layer, like target directions, I need to pay exponential. I need to pay exponential width. Think of this as a lottery ticket mechanism. So I need to initialize a lot of neurons such that one neuron is going to be significantly closer to one target direction that have small an. Otherwise, it's going to be attracted to the big directions. Does this make sense? Okay. So this is an artifact of the correlation loss analysis, because basically all the neurons will be attracted to the big components unless I have exponential width. So this and then this is reflected in the in this condition number dependence in the width. So if the condition number is large, you pay super polynomial compute. Okay. So the two works that I will introduce today will try to circumvent this issue by there's going to be two different strategies. First, we will actually train two layers simultaneously. And the other is using the closed form of the quadratic neural network, and we put a Stiefel constraint on the weights so that they don't collapse to the same direction. All right. So let me talk about the first result, was high information exponent. So now let's just assume we're in this setting. Okay, the high information exponent. So the meaning that we can somewhat replace the sum by the max. So each neuron will go to the closest tutor neuron. So let's let's get rid of the layer-wise training. Okay, let's kind of have some ideal version of training two layers simultaneously. What we do here is that we will normalize the first layer. So there's a typo here. There should be another bracket. So the first layer is normalized. So I'm dividing WI by its norm, but then I'm pulling the norm out. So this is known to be a two homogeneous parameterization. So this is kind of you can think of this as modeling, like jointly training two layers together. If sigma is a ReLU, then this will be true if you have balanced initialization. But sigma is not ReLU, so this is not the most standard parameterization. So now we will not be training two layers simultaneously. Now we will just parameterize the second layer weights as a norm of the first layer. Okay, so this and we'll do gradient descent, like a single stage gradient descent on this two homogeneous neural network. And why does this help us get rid of this exponential condition number dependence? So if you remember, the problem here is that because in the correlation loss, the neurons don't interact. So even if let's assume like AM is very big for 1M, so meaning that all the neurons will go to this single direction. Even if a lot of neurons already recover this direction, it doesn't prevent the remaining neurons from still going to the same direction, because the correlation loss doesn't include any interaction between the neurons. Okay. So, but with this two homogeneous parameterization, what's going to happen is that because we're directly optimizing the squared loss, once you recover one theta m, this target direction, it's going to be deleted from the loss. Okay. So what's going to happen is that after you achieve strong recovery for one direction, the second layer, the norm of this neuron is also going to blow up, and it's going to like fit the norm is going to converge to the second layer coefficient rapidly, so that this term is essentially deleted from the loss. Okay, so now the remaining neurons are no longer attracted to this big direction, and they can converge to somewhere else. Okay, so this will be the mechanism that allows us to get away with having polynomial width. Does this make sense? Okay. So here we have to use interaction between neurons. We have to use the MSE loss for this sort of the deletion sort of mechanism to happen. Okay, so here's the theorem that we can prove for this single phase training. So this is again information exponent greater than 2. We can handle extensive width, but we're a bit sloppy in controlling how big we can take the width to be. So here we take the width to be like a small polynomial, d to the 0.1. So this is not exactly this doesn't cover the setting all up to like linear. But this can be improved, I think, at least to something like 1/4 or a half. So the two statements here, the first is about the emergent risk curve. What it's stating is that the nth neuron is going to be learned exactly at this time. Okay, so meaning that there will be at least one student neuron that achieves strong recovery with theta m at this time. So this time roughly scales with t to the k divided by 2 minus 1, and then there's a learning rate here, and the time depends on the length, the strength of the second layer coefficient. So the second layer is small, then a minus 1 is large, meaning that you have to take longer time to recover this. Okay, and then if you want to learn all the directions, then this is sample complexity you pay. This is so you have the regular, the normal d to the k minus 1 factor, and then there's this condition number dependence, and there's some additional poly m factor that we're not sharp. Just a corollary. So if ignoring polylogs, what this theorem is saying is that if you want to achieve small population MSE, you need something like d to the k minus 1 poly m samples and runtime, and the width of the student model n will just be proportional to m star. So this is like the minimum amount of neuron you need. So this and this is quite important because we want to establish a sharp approximation barrier for the scaling law. And again, for this particular setting, all the prior works, most of the prior works, is going to require either sample size or width that scales exponential in the condition number, which is something like poly d. So here everything is all the complexity here is polynomial. Any questions? Okay. Okay, so now, so for this theorem that I stated, we didn't assume anything about the power law structure. This holds for generic second layer teacher weights. Okay, so now let's assume that the second layer weights follows a power law. So let's say am is like m to the minus beta for beta that's greater than 1/2. So this second layer is square summable. Okay, and so we get roughly the same behavior, but so each neuron is going to be recovered at this time. So now the time is going to also scale with m to the beta power. Okay, and now the population MSE is going to be a sum over these curve. Each of them have a emergence time of this poly d factor times m to the beta. So now if you integrate this tail, you get a scaling law that looks like this. So there are two parts. Remember, capital N is the width of the student model. So we have n to the 1 minus 2 beta. This is going to be the approximation barrier. Okay, this is the width bottleneck. And then there's going to be something that decays with the number of steps you take. So this is the optimization barrier, and there's an exponent that looks like this. Okay, so this is pretty much this illustrated figure I showed earlier. The intuition for these two scaling exponents is very simple. It's just that because we know each direction is learned at a particular time. Okay, so the smaller components are learned at a larger time. So then you can approximate this loss by the sum of a bunch of indicators. And this indicator, you can approximate it with this Riemann integral to give you this power law. Okay. And now, if the width of the student model is less than the width of the teacher, I can learn at most the top n components of the teacher. So that incurs an approximation bottleneck. Discuss with this. So approximation and optimization. Okay. Okay. So here are some figures. So on the left, I have this. This is what the theory predicts in the infinite dimensional limit. So basically, the loss is going to drop every time I recover a new teacher direction, and so it's going to have a sharp drop. And then as you learn more direction, eventually the loss is going to become like a smooth power law up to some approximation barrier. So then the loss stops improving. Okay, so this is a theoretical prediction, and if you run an experiment on learning Hermite 4 neural network, you kind of see something that's qualitatively similar. And the slope kind of matches, but for the empirical curve is have a slightly steeper slope. I think this is because the power laws, sort of the slope is actually increasing due to the finite truncation. Okay.
What kind of nonlinearities would allow this?
Oh, so any information exponent greater than 2. So you need so you need an activation function that's missing the first 2 degrees in the Hermite expansion. This experiment is for Hermite 4.
If I understand, if I remember correctly, Hermite is like a polynomial, right? Like
Yeah.
1 and 2 means you don't have a
Yes.
linear and a quadratic term.
Exactly. Yes. So this means we cannot handle any commonly used activation. ReLU, 10H, everything has, you have to subtract the mean and the quadratic part. Yes. So
the fancy activations like Silu, I don't know.
No. So pretty much any activation function you use is going to have a Hermite 1 component. So I'll speculate at the end of what's going to happen if you include a Hermite 1, but currently I think the most realistic activation that we can handle will be in the second half of the talk is like something like a quadratic. So think of this might handle something like the absolute value activation function, which is ReLU minus the linear part. So that has information exponent.
The phenomena that you described, does it happen for these activations?
So my speculation is the following. So if your activation function have a Hermite 1 component, so all your neurons is going to collapse to the same direction. This is the direction, this is a linear combination of all your teacher neuron. So in the beginning, your loss is going to decrease a little bit. And then after that, you have to somehow break symmetry. And then that requires a higher order Hermite modes. And I think then you will see something similar to this. Okay, so in the beginning, you'll fit the Hermite 1 component, and the neurons will collapse. And after that, as they begin to branch out, you will see something that's similar. Okay, and I guess for the interest of time, I'll skip. So there's some caveat in the learning rate selection, which is that this is kind of intuitive because as I go further down into the scaling curve, I need to be able to resolve the smaller teacher directions, right? Which means that I need to take a smaller learning rate for this martingale analysis to work. So it turns out that the optimal learning rate schedule to some extent is to have a decay learning rate. So you need to, after you learn like the ith component, now you will decay the learning rate accordingly to now, which is now the maximally stable learning rate for the I plus 1. This is something we don't do. So this is why this is a remark that if you discretize in a different way, potentially you'll have a more efficient risk curve. Okay, so let me quickly talk about how this analysis works. So the key insight is still to try to decouple the learning of different directions, because again, we look at the extensive width setting. So the width of the teacher network is infinite dimensional. So like even if you write everything in terms of the summary statistics, this effective dynamics is still infinite dimensional. So this is not something we can easily handle. So you have to basically find a way to try to summarize the summary statistics again somehow. And this decoupling allow you to sort of treat the neurons kind of independently. So at initialization, the different neurons don't interact because the initialization is very small. The key observation is that after a neuron achieves strong recovery with one teacher neuron, the second layer, meaning that the norm of this neuron is going to grow exponentially fast towards this target, which is this AM. This is the norm of the target second layer. And after that, this component of the target function is basically deleted from the loss. And then it does not affect the dynamics anymore. So you have, I think this is analogous to the deflation mechanism in tensor completion. So after you learn a component, you throw it away in the loss. And gradient descent is automatically doing this because of this two homogeneous parameterization. Okay. And then from gradient flow to online SGD, it's a standard martingale analysis. Okay. So that concludes the first part. Any? Okay.
So maybe like just thinking of the role of the large information exponent. So you explained well that kind of to facilitate the analysis, this is important. But is that something, but it's still some class of functions that is essentially particularly chosen to be hard.
Right,
So
right.
it seems a bit like a niche case.
Yeah, I definitely agree. Yeah. So again, for the analysis, it makes life a lot easier because now the different components decouple. Each of the neurons will converge to the closest teacher neuron.
That's the trade-off essentially.
Yeah.
That to enable simpler analysis, but you agree that this kind of, it would be nice to have a more generically looking.
Yes. Indeed. Yeah, so there are two limitations here. One is high information exponent, as you mentioned. The other is that we also assume that teacher neurons all have the same information exponent. So both of them simplify the analysis a lot. So this is a very small subclass of this additive or this type class of two-layer neural network. Right. So handling low information exponent turns out to be a bit annoying. So we ended up writing another paper just to handle the information exponent 2 case, which I'll tell you about. So this thing is, for this, I guess we can consider this as just as a neural network with quadratic activation function. Okay, and empirically you see the same scaling, basically. So this is running experiments with online SGD, this quadratic neural network with like parallel second layer. You see the curve look identical to what I previously showed you. In fact, it even look better because there's less fluctuation. Because lower information exponent is usually optimization takes shorter. So
the different curves again were different what?
This is the same experiment, but just with a quadratic neural network. So this is
But the different colors?
Oh, sorry. So each of these color represent a width. So
different.
Yeah. So for smaller widths, you optimize and then you hit the approximation bottleneck. You don't have enough neuron to learn the remaining target components. So each of the lighter colors are bigger width.
Okay. And what's the target function here?
Oh, this is also quadratic neural network. So everything I told you about will be well specified. So the link function always matches. Right. So empirically, you see the same scaling law. This good behavior. But then the issue is that now you don't have this decoupling going between different directions. So now it's not going to be true a priori that each student neuron will just converge to the biggest teacher neuron. Okay. So this is bad. The nice thing is that if we just specialize ourselves to this one particular activation function, just the quadratic activation, so not general activation with information exponent 2, then there's some nice looking closed form for the population dynamics. This has been used in many prior works. For example, this paper by Martin and this Martin et al. At AI Stats 2 years ago. Here's an example. Let's say I want to track the overlap between the subspace of my teacher network and the student network. Right? So my teacher spans M star-dimensional subspace, and I can define this overlap gram matrix to essentially be how much these two subspace overlaps. Then this subspace is going to the evolution of the subspace is going to be given by this Riccati differential equation, which makes sense because it's a quadratic neural network. So this is a quadratic ODE. So this has a closed form. For this quadratic case, we will, instead of using the decoupling trick for high information exponent, we'll just use a closed form for the population dynamics to do the analysis. Okay, and just based on the closed form, it turns out that the analysis for gradient flow is not too hard. So now this theorem only applies to quadratic link function. The nice thing is now we can be very sharp in terms of we can cover a very general width. So now the width, the teacher width M star is going to be proportional to d theta alpha, and alpha can take anything between 0 and 1. Okay, so this covers all the way from like the small width, like phase retrieval, to the extensive, almost linear width. There's a technical issue that prevents them from going exactly to linear width. Okay, so if beta is greater than 1/2, we can get this risk scaling that's almost identical to what you previously see in the high information exponent case. The only difference is that now the critical timescale is log d. which makes sense because now the time it takes to learn each single index model is going to have only this a log d, not a d to the k divided by 2 plot. Okay, and so this is kind of what the risk curve look like. It's the same as before. It's just that here I'm not plotting the y-axis of log scale. So this is this light tail sort of scaling law we get. We can also handle the heavy tail case where this beta is smaller than 1/2. So now the second layer is not square summable. And in this case, the scaling law looks a bit weird. So the intuition is the following. So in this case, when beta is square summable, that means essentially my target function only have like finite energy. I only need to learn finitely many teacher direction to achieve arbitrarily small loss, constantly small loss. Whereas if the target function doesn't have a square summable second layer, now I have to learn infinitely many directions in order for the loss to decrease. So now the relevant regime becomes a proportional regime. So now the student width and the teacher width should grow together, and this and the ratio converges to this constant. And this constant phi is going to appear in the approximation bottleneck. Okay. So this is what this heavy tail case look like. So essentially, as I make beta smaller, so when beta is very small, I'm looking at this isotropic case, which is, and then this looks like phase retrieval. I'll just get a sharp decrease. And as beta gets larger, it's going to look more and more like this this type of scaling law curve. So at least at the population level, this just by looking at this Riccati ODE, we can get the scaling behavior. Right. Okay. So the discretization turns out to be quite ugly. So at gradient flow level, this works. We get the same scaling law. So there's no reason to think that a standard Euclidean discretization doesn't work. But we were kind of lazy to do the Euclidean discretization. So instead, we do online SGD, but on a Stiefel manifold. Okay. So the Stiefel constraint allows you to stabilize the trajectory. So now the output is always bounded. So discretization becomes easier. So basically, but the annoying thing about Stiefel is that now you're agnostic to the second layer magnitude. So they could, the second layer in AM, they have varying magnitude, but now you can only hope to recover the subspace. That's an M star dimensional subspace. So after that, you have to fine tune. So you have to sort of refit you have to account for the varying second layer coefficients. And the nice thing is that this part is, in terms of sample and computation complexity, this is much less than this. This is phase 1. So this is not a big deal. But the analysis, I think for online SGD, you should get the same scaling law, even if you don't do this layer-wise scheme. So we were just so we're doing this because we're lazy, and the hard part of this SGD discretization is that if you remember in all these earlier like multi-index learning results, we do this martingale decomposition, right? We have this drift part plus some martingale noise that we concentrate. Here, because the problem is extensive width, we need to do the martingale. We need to control the martingale terms in operator norm. Because if my gradient is like a very long vector, like single index model, then it doesn't matter if I'm looking at the operator or the Frobenius norm. It will give me the same rate. But here, I'm looking for something that's infinite time, infinite dimensional. So if I naively look at the Frobenius norm concentration error, and for the martingale, I'm screwed. I will guess where the rates are much worse. So this turns out to be the main technical hurdle. Okay, so for this algorithm, so basically, the theorem states that there's a sufficiently small learning rate under which I can track the population risk, meaning that I will have the same scaling. Okay, so again, for this light tail case, beta greater than 1/2, the learning rate will just be 1/d polylog d. This is the same as what you get for just learning one quadratic neuron. And this gives me a sample complexity of d polylog. Okay, and for this heavy tail regime, now my learning rate needs to scale with d times m star to the beta. And this is probably not optimal, but now the sample complexity becomes m to some power times d. Okay, so let me just provide some interpretation of these rates. So again, in this light tail regime, we're kind of information theoretically optimal because we have this is d polylog d, and you need like D samples even to learn this one quadratic neuron. So this part is pretty sharp. And for the heavy tail case, we are sharp when beta equals 0, which means that there's no power law in the second layer. It's just isotropic. Because now beta 0, we get a sample complexity of D times M star. Okay, and we're trying to recover M star dimensional subspace, so you should get this weight. So this is.
Sorry, Danny, I'm kind of getting confused. How is this related to the gradient flow?
Oh,
In a sense, this should only be worse, and yet you're saying that this is information theoretically optimal, but then
oh, sorry. So
the previous one better? Sorry, I'm a bit like.
sorry, that was I should be more clear. For gradient flow, there's no sample complexity. This is the population gradient flow.
Right.
Yes.
So you only have time and.
Yes, this is time complexity. And now I'm saying that if you set the learning rate to be sufficiently small, now the time we can translate the time complexity to the sample complexity of online SGD. And
I could still think about it as time.
Mhm.
Okay, so you're saying it's information theoretically.
right, this is for the
The
sample.
sample complexity.
Right. This is the sample complexity lower bound.
Okay.
Right. So yes. So thanks. That's a good point. So for example.
But then why is there no dependence on beta then anymore? Why n proportional to t?
It's sort of hidden in this. Well, this polylog could depend on beta, but then the intuition is basically that because beta is greater than 1/2, I only need to learn finitely many directions to in order to achieve arbitrarily small constant loss. So now the dependence on beta is just in this polylog.
But there was before the case as well. Beta was bigger in half, and still you had dependence on t and.
Right. Yes. So here, So this is the scaling law result, and here I guess I should be more explicit. I'm stating this sample complexity result as the complexity required to reach some epsilon loss, and so this and epsilon is a constant.
Okay, so this is not about the scaling.
Right. The scaling law is just this sentence that tells me that I have the same risk scaling as a gradient flow case. Here, when I compare sample complexity, I'm just looking at this how many samples you need to achieve some small.
I see that sentence. I kind of missed that. So you're saying exponents are the same.
Right. And here
This gives you more.
Yes.
This gives you something about the sample. Okay.
Yes. Yes. So everything I'm stating here, like I'm hiding the epsilon dependence. I'm just being lazy. But think of this as the sample size required to achieve some epsilon population loss. Okay. And so that's why I was saying, so because for the light tail case, this is information theoretically optimal because I need sort of D-sampled estimate like D-dimensional vector. And when beta is 0, this is also optimal because I'm estimating D times M directions. And this is the number of samples I need. And one interesting observation here is that, so again, like when M equals 1, M star, this is just phase retrieval. So now there's a log in the sample complexity. So sorry, I should refer to this. So you get D polylog. The interesting observation is that as beta goes to 1, this means that this ratio D divided by M star, this is going to become closer to a constant. And then this log is gone. So meaning that, of course, this is not, sorry. I cannot make this claim rigorous because we cannot exactly cover the linear with regime. I cannot take beta equals 1. But you'll see that this log gradually diminishes, which means that when the width becomes linear, I would just get D squared, not D squared log D. Because this ratio is good. This becomes 1. Okay. So this log kind of starts to diminish as the widths become larger, which makes sense because intuitively this is because this log D search phase appears when you're trying to find some very low dimensional subspace. But as beta become larger, your weight already spans it spans more directions. So this search phase is going to become like shorter. So finally, in this intermediate regime, we're not sharp. The way to see that is, let's say I take beta to be something close to 1/2, and I take M and D to be roughly the same scale, then I get something bigger than D squared, which is stupid because even if I do kernel regression for this quadratic network, I should only need D squared. So, but feature learning should not give you something worse than kernel. So here, this beta dependence is, well, I believe the right scaling should just be D times M in this regime as well, but the analysis give us additional beta effect. This is not. Okay. Okay, so I think I'm actually on time. Let me. Oh,
But then do you still get exponent? What was the claim for the that's smaller than half case? Get the scaling laws? I mean,
oh yes. So for the scaling law, we are still tracking gradient slope. So if you look at if I look at a particular time and how does the loss decay, it's still going to look like this. Right. It's just that this is all hidden in the theorem where I'm looking at like some finite epsilon. Okay. Okay. So, yeah. So basically, the
but
PR.
somehow I expect the sample complexity to be better than quadratic because it will still have so many.
I mean, even in the linear width regime, or you're talking about the suboptimality, right?
Yeah, for beta bigger than 0,
Mhm.
it should be less than quadratic.
Yes. I think it should be still somewhat quadratic because in the sense that you still have to learn infinitely. You still have to learn like proportionally many direction to get non-vanishing loss.
Oh, okay, that was here, this side.
Yeah. So once beta is less than 1/2, now suddenly this like m and n and m star needs to be proportional. So I think it's you would just get m star times d.
Yeah.
Right. But this is clearly suboptimal. And yeah, but anyways, so there's pros and cons between these two analyses. Previously, we do the high information exponent analysis. It's kind of more natural. It's just only a single phase training. We don't have to tweak the algorithm, but the theorem is kind of less covers a more specified regime. So here we can basically do almost all the possible with up to linear, except for the exact linear width regime, and we get more precise scaling results. Okay, so let me sum up. So again, what these two works tell you is that if we're learning a large two-layer neural network with high information exponent activation function, then the recovery of each teacher neuron is going to have this like sharp transitions. But then the overall loss is a sum over these emergent curves, so you get a parallel with a specific exponent. Okay, and I will just mention a few future directions. One is that right now we only have a one parameter scaling law because we assume the data is unstructured. The power law only comes in the second layer of the teacher model. So we could also put a power law on the data and this kind of like source capacity. So then potentially you could get a 2-parameter scaling law. I think we already had discussion over here. For low information exponent, I think my conjecture is just that in the beginning, now you have to deal with timescale separation. In the beginning of training, you'll be dominated by this low information exponent part. And then that's going to collapse all the neurons into one direction. After that, the high information exponent will start to matter, and you might see something similar. Okay, and the third part is what I'm most curious about, which is that this scaling law is kind of, if the most important thing I think is missing in terms of is that the different tasks don't interact. Okay, it's like, although we don't assume the tasks are decoupled a priori, ultimately the analysis works by just showing that they're approximately decoupled. So we're still learning a bunch of independent things. Okay, so we don't have any sort of mechanism that tells you that you start to learn task 3 only after you learn 1 and 2 in some combinatorial way. Okay, so I think in order to get some and this is why we always get the same exponent. So the exponent we get for the scaling law, if you these look like the same exponent you get from linear regression, because the mechanism is roughly the same. You learn a certain component at a certain given time, and then you integrate this. This is a bunch of indicator functions. So in order to get a different looking exponent, I think we might have to go deeper. I think there's some very nice work people here that look at a deeper model, and I think that potentially give you some mechanism that for the compositional scaling. Okay, I think I'll end here.